Okay, so in this video, we want to consider the geometric meaning of the dot product. So consider the following picture. We'll look at vectors as always in R2 in the xy plane or in R3, the three-dimensional space. Imagine that you have two non-zero vectors, say vector u and vector v, and we are going to position the two initial points together, and suppose vector v looks like this. Naturally, we can look at the angle between u and v. And every time you have two vectors, where you position their initial points onto the same point, the angle between the two vectors is always the smaller of the two angles, right? Because you could take this angle right here, or its complement, but we always take the smaller of the two angles. So theta. So of course, theta will always be between 0 and pi. So a natural question is, if I give you two vectors that are algebraic vectors, can you find the angle between the two vectors? And as we will see, we can do so using the dot product. Now before we try to figure out how to connect the vectors with the angle between the two vectors, recall the law of cosines. Right? If I give you an arbitrary triangle, let's draw it here, any triangle. It doesn't have to be a right triangle. Suppose the angle here is theta. We call this side C, we call this side B, A and B. If you recall the law of cosines, it says that C squared, so the side opposite to the angle, C squared, is equal to A squared plus B squared. But there is a correction factor, and that correction factor is minus 2 times AB times the cosine of the angle opposite to edge C. So minus 2AB cosine of theta. And that is the law of cosines. Well, now we have a triangle here. Well, almost. We have two edges, right? But remember that we can easily form a triangle by connecting the endpoints of our two vectors. And if we do vector v plus this vector, we end up with vector u. So this vector ends up being u minus v. Let me just scratch this off. This was our vector v. And this is our vector u. So we now have a triangle, right? This vector added with this vector should give us u, but v plus u minus v is u. So it works out. Now we have a triangle. Let's apply the law of cosines. So the length of the edge opposite to the angle squared, well, the opposite edge of theta is the vector u minus v. So by the law of cosines, the norm of u minus v squared will be the sum of the squares of the other two edges, therefore the norm of u squared, plus the norm of v squared, minus twice of the length of the other two edges, so minus twice the length of u times length of v, times the cosine of the angle opposite to this edge, therefore cosine of the angle, which is theta. Let's try and clean this up a little bit. If you remember, the connection between the norm of a vector squared and the dot product is that if you dot a vector with itself, you get the norm of the vector squared. And this is exactly what we're going to do now. We have the vector u minus v, the norm of this vector squared, but that's just the vector u minus v dotted with itself. Whatever the vector is, if you dot a vector with itself, you have the norm of the vector squared. Let's expand this and see what we get. Recall that the dot product, although it is a vector operation, behaves just like regular scalar multiplication. So we can distribute. We'll have u dot u minus u dot v minus v dot u minus minus plus v dot v. And let's simplify this a little bit. U dot u, well, if we're dotting u with itself, that's the norm of u squared. So that takes care of this one. Plus v dot v, that's the norm of v squared. And if you remember, the dot product commutes. So u dot v, that's the same as v dot u. So we can combine both of these as negative 2 times u dot v. And now, this is again our left-hand side. Norm of u squared plus norm of v squared minus 2 times u dot v. Let's equate this back to the right-hand side and see if we can simplify. So this is our conclusion, or at least we're heading towards our conclusion. The left-hand side of the equality is the norm of u squared plus the norm of v squared minus twice u dot v. And this equals the right-hand side from the law of cosines, which is the norm of u squared plus the norm of v squared minus twice the norm of the two vectors multiplied together times the cosine of the angle between vector u and vector v. And now we can simplify a great deal. Norm of u squared, subtract from both sides, gone. Norm of v squared, subtract from both sides, gone. And we're left with negative 2 times u dot v equals negative 2 times norm of u, norm of v cos of theta. Divide across by negative 2 is gone. And what we're left is remarkably simple, but also quite interesting. If you dot u and v together, we're left with u dot v. Remember, this is a simple algebraic operation. We multiply corresponding components and we add them up. And now look at the right-hand side. If you dot u and v, you will get the length of vector u times the length of vector v, so the product of both norms, times the cosine of the angle between vectors u and v. And this is where the geometry comes in to the dot product. So algebraically again, we multiply corresponding entries of u and v and we add them up. And geometrically, it is the product, if we go back to our picture, it is the product of the norm of u with the norm of v times the cosine of the angle between vectors u and v. And this is the geometry of the dot product. Now, if we wanted the angle between the two vectors, we can easily isolate for cosine of theta, divide by the norm of u norm of v, and so you get that cosine of theta is equal to u dot v over the norm of u times the norm of v. And of course, finally, if you want the angle, take the arc cosine on both sides, and so the angle between two vectors is given by the arc cosine of the dot product between the two vectors over the product of the two norms. So there you go. Let's go back to this now. There are a few key consequences of this equality. The first one is, one thing that we'll see in this course, at least in the next few chapters, is the notion of orthogonality, vectors being perpendicular. And there are a lot of applications to objects being perpendicular. So a question is, if I gave you two vectors in space, and usually we write, and I'll write it here, we usually write u little inverted t v. This signifies that u and v are perpendicular. So only if u and v are perpendicular, and a synonym of perpendicular is the word orthogonal. They are synonyms. So whatever you say perpendicular or orthogonal, same thing. And now think of how simple it is now with the help of the dot product to check whether or not vectors are perpendicular. Right? If vectors are perpendicular, it means of course that the angle between the two vectors is pi over 2. So this is our theta, which is pi over 2. And look now at your dot product. If theta is pi over 2, cosine of pi over 2 is 0. So all of this is 0. Therefore, the dot product is equal to 0. And this is a fantastically simple result. Two vectors are perpendicular if and only if, well, naturally the angle between the two vectors is pi over 2, 90 degrees. Therefore, cos of pi over 2 is 0. Therefore, the dot product is equal to 0. So that is one really neat consequence of the dot product. Whenever you want to check whether or not two vectors are perpendicular or orthogonal, dot the two vectors, and if the dot product is 0, the vectors are perpendicular. If the dot product is not 0, the vectors are not perpendicular. Simply coming from this equality. Now another thing worth mentioning, and this is the so-called Kashischwarz inequality, which follows directly from what we have just derived. So recall that if you dot two vectors together, algebraically we multiply the corresponding entries and we add them up. But geometrically, this is the length of the first vector times the length of the second vector times the cosine of the angle between the two vectors. And now here's the following so-called Cauchy-Schwarz inequality. From this equality, it will be rather trivial, but later on we'll prove it that it also works with vectors in R4, R5, and in general for Rn for any given n. And this will be a lot less trivial. But for now, let's just state what the equality is, and then we'll prove it given this equality, this equality. Sorry. So this is called the Cauchy-Schwarz inequality. And what it says is actually quite simple. In absolute value, the dot product between u and v, and recall that the dot product is again a real number. In absolute value, this can never exceed the product of the two norms of both vectors. So if you dot u and v and take the absolute value of this, it will never be bigger than the norm of u times the norm of v. Let's prove this with this equality, and the proof will be essentially just two lines. Well, we have the left-hand side, the norm, or I should say the absolute value of u dotted with v equals, let's replace u dot v by this expression, absolute value of the norm of u, norm of v, times the cosine of the angle between u and v. But the absolute value makes negative quantities positive, or at least non-negative, but the length of a vector is always non-negative, so we can drop the absolute value from the two norms. So norm of u times norm of v. But the cosine could be negative, so we leave the absolute value on cosine of theta. And now quite simply, cos of theta is always between -1 and 1 for any angle. Therefore, in absolute value, cos of theta can never exceed 1. So if we replace this by its largest possible value of 1, the whole expression becomes bigger, and we're left with norm of u times norm of v times 1, which is just norm of u times norm of v. And this completes the proof. The absolute value of the dot product will never exceed the product of the two norms of the vectors. And this is called the Kashischwarz inequality. And right now, all we have is this is true, but it depended on this equality being true, and we only have this equality for vectors right now in R2 or R3. So this is worth mentioning. In R2 or R3. Or I should say not or, but and. If you have a vector with 2 or 3 components, the inequality is valid. As we will show later, the equality is still valid no matter how many components your vectors may have. In our next video, we are going to consider an application of the dot product, keeping in mind that we have two vectors being perpendicular if and only if they have a zero dot product, and we'll apply this notion of orthogonality to problems of distances.